Hi everybody, my name is Stéphane Ethier. I work at the Princeton Plasma Physics Lab. We work on magnetic confinement fusion. This is our main mission, which basically we're trying to create a star-like conditions inside a device that we call a tokamak. Essentially, you have a plasma, so an ionized gas in there that we heat up to 100 million degrees, but the wall of the machine itself had, it can't be more than 100 degrees plus, a few hundred degrees. So how do we do that? Is with strong magnetic fields to confine the plasma inside that machine and prevent it from touching the walls. But you can imagine that, you have 100 million degrees. Let me get the laser pointer here. You have 100 million degrees inside in the middle of the machine there. And at the walls, you have a few hundred degrees, like 300, 400 degrees. So the gradients of temperatures and also of densities are extremely high. So that leads to very interesting physics that you can study with various codes. And we do have a whole battery of codes, like magnetohydrodynamics codes to study the fluid-like plasma and magnetic field evolution. And we have wave heating codes, but in particular, in what I've been working on for most of my career is on kinetic codes, and in particular particle and cell codes. But you can also have mesh-based, purely mesh-based codes to that do the same, solve the same kinetic equations. And this is to study velocity-dependent physics, such as turbulence or wave-particle resonances. And here, waves, we talk about the fields. We have electromagnetic fields in the machine, and you have ions and electrons, and they interact with each other. And depending on the velocity of the ions and the electrons, they interact different ways. And you have magnetic trappings of these particles, like lots of nice physics in there. And because of those magnetic fields, just like to point out that there's a type of kinetic equations that we solve that's fairly specific to the fusion community, MFE community, and gyrokinetics. I'm not going to go into detail, but if you're curious, you can look it up. All right, but we're called the Plasma Physics Lab. So essentially, we do study pretty much everything related to plasma as well. So we do study space plasmas, heliophysics, which is physics of the sun, solar flares, magnetic reconnection, plasma propulsions for satellite and spaceships, and industrial plasmas. And here I bolded this because plasma processes in microchips fabrication is a fairly hot topic these days. And there is a strong need to have 6D particle and cell codes to study the kinetics inside these devices. And there's a lot of rich chemistry that's involved in those machines. The plasmas are not completely ionized. There's neutral gas as well. So it's a very complex problem that requires kinetic codes. And when I say 6D, there is three dimensions in space and 3 dimensions in velocities. So let's talk about the code. So I've worked with several particle and cell codes along the way, and particularly to put on GPU. One of them is the Gyrokinetic Tokamak Simulation code, GTS, which was ported to GPU using OpenACC during the 2019 Princeton Hackathon. Thanks for Julia and Tom for organizing these hackathons. They're great. And this code is a 5D gyrokinetic particle and cell code. And it's to study microturbulence in the core plasma of the tokamak. Basically, everything that's inside and that has this 100 million degree plasma is where the core is. It's a little over 10,000 lines of FORTRAN and some C. It has MPI plus OpenMP parallelism. And what we did is the particle routines have been ported to GPU with OpenACC, and that was fairly straightforward because as you all know and love OpenACC, it's supposed to be fairly simple. I mean, you have to know what to do and you have to know how the GPU works, but it's a lot easier than doing CUDA. One thing that I can point out about particle and cell code in general is that the charge accumulation, so the step where you have, so in PIC codes you have a grid and you have the particles, and at each time step you have to put those particles, you have to accumulate the charge of the particles, or the charged particles on the grid. And that step requires atomic operation. So there's a lot of conflicts in memory. So on the CPU side, when we do OpenMP, it's fairly straightforward to just use a private copy of that grid for each thread, OpenMP threads. We have something like 16 or 32, and there's plenty of memory on the CPUs now to handle that. But when you get to the GPU, you can't have a private copy of the grid for each thread. There are just too many of them, right? So you really depend on atomics, and the faster these atomics are implemented in both the hardware and the software, the faster your code will go. Just to say, that's the team that participated in the hackathon, and a lot of the work was done by postdoc Chenhao Ma and Minggu Yu. Chenhao now works at Google. Minggu is still at PPL, doing some good work. So next code that we had, oops. Oh, wait. So just to give you a little bit of the speed up that we got, these are different steps in the code having to do with particles or the field solve. Field solve was still on CPU, so there's no speed up there. But overall, on the P9 plus 4 V100 GPUs, we got a decent speed up, 8 times or something like that in total, which we're happy with. And the code now runs in production on our GPU machine at Princeton, which is called Traverse. All right. Next code is the low temperature plasma PIC, LTP-PIC, which was ported to GPU, again with OpenACC during the June 2020 Princeton hackathon. Team member, just an interesting fact, the graduate student who wrote that code, Tasman Poes, was back home in Australia when we had the hackathon, so he had to get up in the middle of the night and work on the code. So, but he was a good sport and he did a lot of good work. So this code is a full 6D PIC code to study low temperature plasmas for industrial applications, including propulsion. It's written in C, pure C, with MPI plus OpenMP hybrid parallelism. So, domain decomposition with MPI, with also particle coloring scheme, and OpenMP at the loop level parallelism. So, but as the GTS code, it's a PIC code as well, the charge accumulation step also depends on fast atomic operations. So definitely for PIC, what we tell all the vendors in implementing GPUs is like, please give us fast atomic operation. Now, that because of all the chemistry that needs to be done and the collisions that need to be implemented in that code, there is a need for a very high quality pseudo-random number generator on GPU. And the ones that were available were not actually cutting it. So as part of this hackathon, one of the members ported a Mersenne twister algorithm code to the GPU using OpenACC, and that was very successful as well. We also studied the GPU performance was high per solver. Like I mentioned that all the field solves, so you put your particle charge on the grid, and once you have the field on the grid, you use a solver, linear solver, to get the fields. But there's a lot less parallelism in the grid, and the amount of communication, MPI communications involved in doing the solves is pretty high. So any solver that we've tried, it's very difficult to get high GPU performance on the field solve. So normally we just keep that on the CPU. Hopefully that will change in the future. And thanks to our mentors from NVIDIA, Matt and Moshgan, for helping us with that project. We had a lot of fun. This is the kind of speed up that we managed to get. It was very respectable. So here, this is compared to Traverse, which is our P9 plus 4 V100 GPUs, and we compare to just using the P9 processor CPUs. And Stellar is our brand new 96 core per node Intel Cascade Lake, which we get nice speed up compared to just the Traverse CPUs. But definitely with the GPU, we get very nice, almost 20x speed up for that code. Now let's move to the big code. So another project that I worked with is the XGC project, which is our flagship exascale-worthy code. It's a 5D full device gyrokinetic PIC code to study the age physics in the tokamaks. But to do that, actually, we need that code solves the whole device. I mean, everything you see in the tokamak, that's the volume. And the simulation domain includes everything, even past what we call the separatrix. So if you see this line here, inside that is the core plasma, where the magnetic field has a nice closed flux surface. But once you get across this separatrix, the field lines open, and that's where you have extremely large gradients. And once you hit the wall here, which is that shape we see here, that's where the temperature also goes down a lot. So there's a lot of interesting physics there, very difficult to simulate. And because of that, that code requires from 10 to 100 times more particles than the GTS codes that I showed before. So you have up to something like from 5,000 to 10,000 particles per cell for a code like this. Now, this code was originally written in Fortran 90, and like our other code, it uses a multi-level MPI, domain decomposition, particle distribution, and OpenMP hybrid, parallel algorithm, OpenMP at the loop level on the CPU. And this is always the first PPPL code that's ported to new HPC hardware. And this is the team here. Now, just to go back to the first time that we ported that code to GPUs, originally on Titan. So it was one of the early science codes on Titan. It was ported with using CUDA FORTRAN for the particle routines and OpenACC for the collision routines. And most of the implementation was done by postdoc Steve Abbott at OLCF. Now Steve went on to work at NVIDIA, and now he's at HPE Cray. And Yi-Sung Yoon, who was at Rensselaer Polytechnic Institute, who did the collisions, and the rest of the team there who worked on that. Now for each Titan node, we had one MPI task, 16 OpenMP threads, and we had that one Kepler GPU, which had only 6 gigabytes of memory. So we had to be fairly inventive to deal with that amount of memory and try to do the size of the simulations that we had to do. So we had algorithms like concurrently pushing the electrons on the GPU while we were pushing the ions on the CPU. And because the electrons are so much lighter than the ions, we had to push them. We had to do about 40 to 60 steps of the electrons for one ion step. So you had the electrons on the GPU that were just like moving, and tons of calculations were being done while the ions were being pushed on the CPU. And that worked really well. For the collision routine, each OpenMP thread would actually launch a GPU kernel on a different stream with OpenACC async. Now, because the way the routine was written, there was a lot of work, but not enough to really saturate the GPU. So the way that we found to saturate the GPU was to just use the stream to overlap and send as many kernels as we could on that single GPU. The type of code that we use for that looks pretty much like this. It's not the whole detail, of course, but in one file you would have your OpenMP. So that file would be compiled with OpenMP and the compiler. And the compiler was a PGI compiler, of course. So you would split the loop that would call this fCollision routine. This is a loop over the mesh points. If you see here on the right, you have a cross-section of one of the planes in XGC. So that plane is on a few MPI processes. So each point on that grid would have a calculation of collisions. And so now you distribute all these points between the threads. So on Titan, it was 16 threads. And then in a different file that was compiled for OpenACC, you would check what your thread ID was, and you use that to choose your stream. And then you move the data or create the arrays that you needed to create on that stream, and then start a kernel also on the same stream. And then you would do your loop. This is a loop over a velocity grid there. And so you have 16 threads launching these kernels, and at the end you just wait for everything to come back. So that worked really well, and we were happy with that, and we ran many years on Titan with that algorithm. And then Summit arrived, and the exascale computing project as well. What happened is that the upcoming exascale system basically forced us to rethink our approach, because the XGC is the main code in the ECP whole device modeling app project. That code needs to run on the exascale systems on day one when the machine comes online. So, and basically CUDA FORTRAN and OpenACC are not an option at this point. So, or at least when we had to make a decision, we didn't see OpenACC or CUDA FORTRAN as a possibility. So we decided to let somebody else figure out those details, and we opted for Cocos as the interface to the various hardware, because it has many backends, right? It has a CUDA backend, HIP, SICL, OpenMP target, whichever works for the machine will be on. And right, this is Aurora with Intel GPU and Frontier with AMD GPU. And part of that decision was done because we were also part of in another ECP project that's called the COPA, the Co-Design Project for Particle Applications. And that project developed that Cabana library, which is based on Cocos, and we use that in XGC. But these are all C++ code, so we needed interface, and Cabana has a interface to Fortran code. So through calling from Fortran, you call the C++ wrapper that calls Cocos, and it works. It worked fine, but we wanted to simplify the code and realized pretty quickly that rewriting the whole code in C++ would avoid these interfaces. And we had somebody, Aaron Scheinberg, who was willing to do it. He was at PPL at the time. Now he has his own company, but he's in the process of changing and rewriting the whole code in C++. And now we're using that Havana and Cocos. So we're not using OpenACC anymore in that code because of that. But I would argue that for all the other Fortran codes that we have and C codes that are using OpenACC, we would still love to keep using it, and we will, unless it's not available and OpenMP target offload becomes the better approach, let's say, or the faster code approach. And but that's not up to us in that sense. And from where I'm sitting as a developer, I find that the compiler developers and vendors seems to be pushing for OpenMP offload these days. So we'll see what happens with that. But OpenMP, the implementations are not that stable yet, and good performance is harder to achieve, especially on the new hardware. And I'm sure that Michael Wolf would agree with me that specification is not the same as implementation. So even if it's written in the specification that you can do this, doesn't mean that the compiler can actually make it happen. So it needs a while. It needs time for a compiler to become mature. And right now, NVHPC SDK is really mature for OpenACC. Now, hopefully, it will be for OpenMP pretty soon. On top of it, there's this new descriptive model that's being encouraged, and Michael actually talked about that in his last slide. And I'm going to give you an example here, which looks like his example.
Stéphane, yep. Hate to interrupt. We have a few minutes to wrap up.
Okay, I'll be quick. So basically, the difference is between a code that's not quite portable. You need to use if-defs, and if you want to do on GPU, if you use the OpenMP target teams distribute, as opposed to team loops, which is portable, or in that sense, to give more freedom to the compiler vendors. I love that, and it actually works better. It's gives better performance. The only issue is that I want to make sure that the other vendors and other compiler developers follow suit and really adopt that model as well. Okay, last words. Have we achieved portability yet? Well, not quite, but we're trying. And this is because the new hardware always brings new challenges to implementers and compiler developers. As I mentioned, for both OpenACC and OpenMP, specification is not equal to implementation. So you always have to deal with that. The OpenMP target teams loop seems like a really good way to give flexibility to compiler developers and to implement and give the best performing version of OpenMP offload. Hopefully this will be adopted. A few others have mentioned that base languages should adopt, should support parallelism and offloading to GPU, and that should really happen. And for C++ codes, we find that Cocos is really a good alternative, but we still love OpenACC and OpenMP for Fortran and C codes. So thank you.